During my practice streams, I did a lot of problems, and I don't want to make a video for every single problem because some of them weren't that interesting and some of them are rather small and don't need a full video. So I'm skipping over problem number 4, and in this video I'm going to cover problems number 5, 6, and 7 from those streams. And this is going to cover some quick mathematical topics, least common multiple calculations, how to derive a formula for sort of a repeated sum pattern, and then we're going to extend the prime listing work that we did in the first prime video, which was the previous one, and get a different solution for a different problem that also involves generating primes and getting prime numbers. Each one of these will be pretty quick, but I think that they're interesting to talk about at least a little bit, so let's get into it. It says 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? So first thought is, let's think of an easy way to get a number that is divisible by a bunch of other numbers. So for instance, if I want a number that's divisible by 1 through 10, all the integers 1 through 10, then I can just multiply all the integers 1 through 10, and I get a number, and whatever that number is, it's definitely divisible by all of those other numbers that I multiplied together to create it in the first place. Now, just doing that is going to make a number that's too big, because, for instance, if we look at just these numbers here, the 2 is very redundant. I could already have a number that's divisible by 2 if I didn't include the 2 in the multiplication, because I'm also including 4, 6, 8, and 10, which will also all make it possible to divide that number by 2. And so if I'm going to try to find the smallest number, I need to be able to eliminate factors from the multiplication that are redundant. And so in order to think about that, I want to start by looking at the factorization of all of the numbers that I have written down here. So I'm going to look at the factorization of the numbers 1 through 10 and the factorization of x. Now this example came from the original problem. They told us that the smallest number which can be divided by all of the integers 1 through 10 is 2,520. So I'm going to write that one side by side with everything we have so far and factorize it, and that will let me highlight what we actually need, which is not the multiplication of all of these numbers, but something derived from the factorization of all of these numbers. So what I actually need is to look at each of the individual primes and grab the highest power that covers all of the numbers in my list. So for instance, if I look at all of the numbers that have a multiple of 2, the one with the highest power is 8, which has a factor of 2 to the 3. Right? All of the other even numbers have lower factors of 2, or lower powers in their factor of 2, so I don't need more than 2 to the 3 to handle anything else, and therefore a 2 to the 3 in the final number will guarantee that the 2 factor is covered across the board. Similarly, I need a 3 squared to handle the 9, and that 3 squared is also enough to handle the 6 and the 3, and then I need a 5 and a 7. So multiplying just those highest powers together, I get a much smaller number with lower powers for the 2 and the 3 factor, and that gives me the 2,520 answer. This object is called the least common multiple of the numbers 1 through 10. So what we're really going to try to do is create a quick and easy tool to build a least common multiple by iterating the numbers 1 through 10, or to actually solve the problem, the numbers 1 through 20. So from there, what I wanted to think about is, how do I get the least common multiple as something I can compute? And I decided to focus on taking the least common multiple of 2 numbers, because it would turn out that if I can get a least common multiple for 2 numbers, then I can iterate that on a sequence and sort of build up a least common multiple for multiple numbers. So to get it for 2 numbers, I just need to think about the prime factorization of 2 numbers and combining those prime factorizations in such a way that I get the maximum power from each individual prime factor into the final result, right? I'm going to combine those max powers together. And what I'm going to rely on is the fact that I can rewrite a max as the sum of 2 numbers minus the min. So let me take a minute to it isn't that hard to think through, but just to sort of think about this, if I have 2 numbers and I add them together, I have a large number and a small number. I don't know which one is large and which one is small, but if I add them together and then I subtract out the small one, then what I have left must be the big one, right? So that's the idea of this formula. And if I can get the min of the powers of 2 numbers, then I can, compute the max by using this trick. So I can get the sum of 2 powers by just doing normal multiplication of a and b, because when you multiply 2 numbers, the prime factors, their powers add together. I can then subtract out anything by dividing by it, and the way to get the min is actually a flip side of the least common multiple is the greatest common divisor. That gives you the min of all the powers of the two input numbers, all combined together into one number. So if I can take a product of a and b and a greatest common divisor, or GCD, of a and b, and then divide those two things, that'll give me my least common multiple function. In order to compute the GCD, we just need to use the Euclidean algorithm, which I'm not going to go over in detail here because it's already a very well-documented algorithm that you can learn more about anywhere. So why don't we take these ideas and move them over to programming mode and get this problem solved now. The sum of the squares of the first 10 natural numbers is 1 squared plus 2 squared plus equals 385. The square of the sum of the first 10 natural numbers, so you see they've inverted here, it's the square of the sum rather than the sum of the squares. The square of the sum is 1 plus 2 plus squared equals 55 squared, so adding those up first, then squaring, you get this much bigger thing, 3025. And then the difference between them is 2,640. So there's the gap between squaring first and squaring second is this amount. Find the difference between the sum of the squares of the sum of the squares of the first 100 natural numbers and the square of the sum. So we're doing the same thing, finding the absolute value of the difference between these two expressions for the first 100 natural numbers. So half of this problem we kind of already have a solution to because we did triangle numbers already. So when we take something like 1 plus 2 plus 3 plus 4 all the way up to 10 or 100, that's a triangle number. And then all we have to do is take our triangle number and then square it when we're done to compute the square of some part of this problem. So that part is handled. What's new here is the sum of the squares. So 1 squared plus 2 squared plus 3 squared and so on up until some n squared. That's the thing we need a new formula for. So we're trying to find a closed form way to compute this, or some way to do a computation of this that is quick and doesn't involve n iterations. And I'm sure that if I just looked it up online, I would have found an answer pretty easily. It's not a particularly unusual or esoteric kind of polynomial solving problem that we're looking at here. But I'd like to practice doing this by hand so that I've got techniques that I'm comfortable with using when less common stuff comes up and I just want to get it right on my own. So to that end, I start with a justified guess that the closed form formula for this sum of squares is going to be a cubic polynomial. And the justification for that guess is just from looking at how a few examples of the outputs from increasing n look and how they appear to behave the way I would expect a cubic polynomial to behave. Next, what I need is some sort of equation on the function that'll give me an extra constraint to work with. So I use the definition that we're using sort of sums of squares to come up with this relatively straightforward fact about the function, and that's going to end up being enough to constrain the possibility space of this function with this one equation. And from there, I can start solving for the constants that make up my cubic. So with some algebra work, we come up with this closed form formula for our sum of squares function. And now we just have to go and implement that in assembly, and we have solved the problem. By listing the first 6 primes, 2, 3, 5, 7, 11, and 13, we can see that the 6th prime is 13. What is the 10,001st prime number? So to think about what I'm doing in my solution to this problem, I'm going to start by analyzing the way the information flows through the system that I already have and how I want to extend it. So the flow I already have is that I have a function called the seive that we wrote previously that takes in an n, which is the maximum number we're going to scan up to, and finds all the primes up to n, and it returns that list of primes. Now, the way I want to be able to extend it is to take the list I already have and to put in a new range of n values where the small number in the range is whatever n I stopped at. So if I stopped at 1,000, then I want to resume from 1,000 and go up to some new upper bound. And I want to generate a new list, which is all of the primes inside the new range. So I won't be generating a copy of the list of primes I already have. I'll just be generating the extension list for the new primes in the new range. And that way I have a way to say, if I didn't get to a prime large enough for what I need, I can go farther without having to redo the first part of the sieve when I want to extend the list. The next thing I want to think through is I have this idea for a function that takes in a list of primes and a little bit of other information and generates another list of primes. And I want to think about how I'm going to be able to iterate that. So once I have 2 lists of primes where the first list is the original list I had and the next list is an extension list, I would hope that I could concatenate them together and form one list that was the list of all primes starting from 2 and going all the way up to the end of the second range, right? Because then I could use that list as the input to another iteration and extend arbitrarily until I'm done rather than just getting one chance to extend. So in other words, I kind of want to be able to make sure that the output type feeds back into the input type nicely. And so when I sketch out how that's going to work, I obviously have to deal with the other detail here, which is how will the concat of these lists work? How will I take 2 lists that are separate lists and merge them into one list that are sort of joined end to end? And the issue this raises is if I just do a simple array, then the join will involve an entire extra buffer copy. But I obviously don't want to do something like stick all of my primes into one giant linked list where each number gets its own node, because I'm going to be generating like thousands, even millions of these sometimes. So I don't know if millions is actually correct. I have to think about it. But either way, I'm generating at least tens of thousands of these to solve this particular problem. And so I don't want a linked list of that many elements, right? So how can I get the best of both worlds? Well, that's what I want to solve in this particular problem, is using a slightly more interesting data structure. And the data structure I end up going with here is kind of the most obvious evolution of what we already have. We will use an array to get the output of one step of the sieve or one extension to the sieve, and then we'll use a linked list to chain together each of those arrays. So I can get big blocks of maybe 1,000 or so primes in each step. However many primes you end up getting when you put in an n, you don't really know how many primes you'll get. So it's a variable length buffer. We don't get to say how far we want the buffer to go. We get to say what we want n to be, and the buffer turns out being a little plus or minus what we would like it to be. And then we have a linked list, and hopefully we can tune it so that our buffers are big and they contain they can be processed as big batches, big chunks, and the linked list is short. So there's only a few nodes in the linked list. In order to get very high numbers here, we want to avoid growing the list lots of times in small steps and instead try to tune things so that we get a few links in the linked list and lots of data in each node of the list. So that's the plan, and now let's take a look at the details that come up when I'm actually programming it. One thing that came up for the first time while solving this problem was that I had 5 parameters. Up until now, I hadn't had that many parameters in a function that I was writing in assembly, and this is a significant issue because the way you pass parameters in a procedure in assembly is by filling out the registers, but there are only a finite number of registers. So when you run out of those registers that are designated for parameter passing, the rest of the parameters have to be passed by putting them on the stack and reading them off the stack. Now, since I'm writing the assembly that implements the function, I have to do the side that reads stuff off the stack, and I have to actually try to do a little digging here to figure out where the correct place on the stack is for me to read out my parameter. So it turns out that there's a few things on the stack when a call happens. The very first thing on the stack is always the return instruction pointer. That's put there by the machine itself when you use the call instruction, and that's how the machine knows where to go back to when you call the ret instruction. This points it back to where the code was right after the call instruction happened, right? Like where does the code resume in the previous call? And the next 4 slots on the stack, and when I say slot, I mean like a pointer size thing. So in 64-bit land, we're talking about 64-bit slots or 8-byte slots. So the first slot is that return instruction pointer. The next 4 slots are reserved for the first 4 parameters, which is a little weird, but it is the way things are set up in the Windows ABI, which is just, even though they're being passed by registers already, space is reserved for them on the stack too. The rules are a little weird. The space doesn't actually have to get filled with the parameters. It just has to be reserved for them, and you always reserve 4 slots even if there aren't 4 parameters. It's kind of strange, but that's what the ABI says. And then if there's a 5th or more parameters, then they are even further than that. So I have to read past the first 5 slots, 1 for the instruction pointer and 4 for the first 4 parameters. And that's where I find the 5th parameter. So in decimal notation, that would be 32 for 4 slots plus 8 more, 40 bytes to go in. In hexadecimal, it's 28. So you can see right here, to read my 5th parameter, I am reading off of RSP plus 28 in hexadecimal.